Hello, welcome to Forest Learn. In this video, we'll be looking at common forces that are present in questions on mechanics. You may have some familiarity with the forces we'll discuss, but even so, there are some subtleties we'll touch on which you may be unaware of. Throughout, we'll be looking at examples of where these forces are present, and you'll also have a chance to test your understanding on a few questions at the end. The forces we'll be discussing are weight, the normal reaction force, applied forces, and friction. It's important to note that these forces are all different types of forces. If you're unsure what this means, it'd be best for you to check out the video we've created on the basics of forces before you watch this one. Also, this is not a complete list of forces in mechanics. We'll also discuss other forces such as tension, drag or air resistance, and upthrust in future videos. Let's start by discussing weight. Weight is the name of the gravitational force of attraction that large masses, such as the Earth, exert on objects. To calculate the weight of an object in newtons, we simply need to multiply the mass of the object in kilograms by the gravitational field strength, G, in newtons per kilogram. So on Earth, the gravitational field strength is 9.81 newtons per kilogram. For example, for a tennis ball in midair, we would show the weight of the tennis ball as drawn in the diagram. Note that we label the weight of an object with the letter W. The weight acts downwards because the Earth exerts a gravitational pull on the ball towards the Earth. To calculate the weight of the tennis ball, we of course need to know its mass. And a tennis ball, at least those used in professional competitions, has a mass of roughly 0.058 kilograms. And so to work out the weight of such a tennis ball, we simply take that mass and multiply by the gravitational field strength on the Earth, 9.81 newtons per kilogram, to get a weight of 0.57 newtons. It's really important to remember that weight and mass aren't the same thing, even though they're mixed up in everyday language. Had we considered the tennis ball on the moon instead of on the Earth, its mass would have been exactly the same, so 0.058 kilograms. However, its weight would have decreased, or would have been smaller than on the Earth, because the gravitational field strength of the moon is only 1.62 newtons per kilogram, resulting in a weight of 0.094 newtons. The normal reaction force is a force exerted by surfaces on bodies when they are in contact with each other. For example, if we have a box at rest on the ground, as shown here, the ground exerts an upwards normal reaction force on the box, as shown here by this upwards pointing vector. It's labeled N, but often you'll see the normal reaction force sometimes labeled as R. The word normal, when used in maths, means perpendicular or at 90 degrees. In other words, the normal reaction force acts at 90 degrees to the surface, which in this case here is just the ground. The normal reaction force can also be exerted by curved surfaces. For example, if we have a marble, shown by this filled black circle, sitting on the inside of a circular ring, then the marble would experience an upwards normal reaction force as shown. Notice the dashed lines that have been drawn. Those dashed lines represent the tangent to the circle at this position here, where the marble makes contact with the circle or the ring. The normal reaction force is again at 90 degrees to this tangent. If the marble were to be moving around the circle or the ring, then at these various positions shown here, it would experience a normal reaction force. And again at these two positions here, the normal reaction forces drawn are at 90 degrees to their respective tangents. Applied forces are pushes or pulls that people exert on objects. So for example, a person pushing a box, as shown in this diagram here, that's an example of an applied force. The applied force is shown by this vector drawn here to the right. Another example of applied forces is when a person lifts something heavy. The applied forces that this person's hands are applying to this object are drawn by these two upwards vectors. Let's move on to friction. Friction is an opposing force that surfaces exert on bodies that are either moving or are at rest but being attempted to move. Looking at the previous example of a person pushing a box, if the box remains at rest, the ground must be exerting an equal force of friction on the box to the left. The force of friction is shown by the vector drawn in black, acting at the bottom down here. If the person were to gradually reduce the push or the applied force that they exert on the box, then the force of friction will also mirror this and gradually reduce as well, and it will become zero when the applied force that the person applies on the box is zero. Returning to the original scenario, if the person were to increase the applied force on the box, there would come a point where the applied force would be bigger than friction, and the box would start moving to the right. If the person were to then stop applying a force, the force of friction would remain on the box as it continued to move to the right and eventually come to a rest. Rough surfaces exert friction, and in reality, all surfaces are rough. However, we might talk about idealized smooth surfaces, such as ice, where we can justifiably neglect or disregard friction to simplify matters. In this video, we'll be assuming that all surfaces are rough. Let's now take a look at a couple of examples involving multiple forces. After this, you can have a go at answering a couple of questions yourself. In our first example, we're back to the scenario of a person applying a force on a box, and the box is at rest, and the force of friction acts on the box to the left. Along with these two forces, two further forces would be acting on the box, namely the weight of the box, which of course just acts downwards, and the normal reaction force that the ground exerts on the box upwards. For our second example, consider a ladder resting against a wall. The ladder of course has a weight, which acts downwards, and because it's in contact with the ground and the wall, these two surfaces exert normal reaction forces on the ladder, labeled N1, that's the normal reaction force that the ground exerts on the ladder upwards, and N2, that's the normal reaction force that the wall exerts on the ladder. And notice that N1 and N2 are both at 90 degrees to their respective surfaces. Remember that the word normal in maths means 90 degrees or perpendicular. Now, this force N2, it's in a sense attempting to move the ladder to the right. But of course, the ladder's at rest, so there must be something which counterbalances this normal reaction force. And that something is a force of friction that we're calling F1 that the ground exerts on the bottom of the ladder. Remember, the force of friction can act on moving bodies, but it can also act on bodies that are at rest but being attempted to move. And that's exactly what we've got going on here. Similarly, the weight of the ladder is in a sense trying to move or drag the ladder downwards. And so there has to be something which is balancing that. Now that's partly balanced by this normal reaction force here, but that's not enough if you look at the size of this compared to the weight. It turns out that there must be a second force of friction, F2, that the wall exerts on the top of the ladder upwards here. The combination of F2 and N1 is what balances the weight of the ladder and stops the ladder from falling down. Alright, so now it's time for you to have a go at a couple of questions. In this first question, there's a box sitting at rest on a slope, or what's known also as an inclined plane. And your job here is to try and figure out the forces that are acting on this box. So please pause the video here and have a think about this, and when you're done, unpause the video and we'll discuss the solution. Okay, welcome back. So in this situation here, there are just three forces acting on the box. Its weight, there's the normal reaction force that the slope or the inclined plane exerts on the box, and again, once again, this normal reaction force acts at 90 degrees to the surface. And there's also the force of friction that the surface exerts on the box up the slope. And this force of friction is what stops the box from sliding down the slope. Okay, so in the second question, we're back to the example we were looking at earlier of a marble, shown as this black circle, moving on the interior of this ring or circle. And the marble is moving anti-clockwise around this ring, as shown by this arrow here. So once again, your task is to try and figure out the forces that act on this marble as it moves. So please pause the video and have a think of this by yourself. When you're done, unpause it and we'll again discuss the solution. Okay, so welcome back. The marble has, of course, a weight acting downwards, and it's in contact with the ring. Now, the ring is a curved surface, which means we should draw in a tangent at the point where the marble makes contact with the surface. With this tangent drawn, we now know that the normal reaction force that the interior of the ring exerts on the marble will simply act at right angles to the tangent. Now the marble, since it's moving anti-clockwise, we can say that when it's at this point here, its momentary or instantaneous velocity is parallel to this tangent. You can imagine that its direction of motion here, at this instant here, is along the tangent and downwards. So if that's its direction of motion, then this surface, the interior of the ring, will exert a frictional force which acts opposite to the direction in which the marble is moving at this point here. So this friction force is simply just opposing the motion of the marble when it's at this point here. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment. I'd love to hear from you. Thank you for listening, and I hope to see you soon.